So we'd like to go over some of the problems we proposed for review. And I have all the problems here. There are 8 problems in that sheet. So to start, I would like to do those, but I don't want to do them in the order they are. I would like you to suggest what problems are giving you the most trouble. Which ones do you want to see first? 8. So we're going to find the max and the min of a function on a region, on an ellipse in this case. So here's how you set it up. We have f, it's x squared plus y, and my function g is x squared plus 2y squared equals 8. So I want to maximize f in the curve that is given by g. The method of Lagrange multipliers tells me that this will happen, the max and the min will happen where the vectors, which is the gradients, are actually parallel. So first, let's find what is the gradient of f. The gradient of f with respect to x, that's 2x. With respect to y, it's just 1. The gradient of g is 2x and 4y. Okay? So what I want to solve is for the gradients to be parallel, and it's still g equals 8. Okay? We still have to live on that ellipse. Now, by the way, the lambda can be in either side. Okay? So if for whatever reason you want the lambda on a particular side of the equation, so you don't have to work with 1 over lambda and things like that, you can actually set this as lambda f is as nabla f is nabla g. Okay? Which in this case might actually help, because this other form tells me that this sets up 2 equations, that this has to be equal to this and this has to be equal to that. So it tells me that 2x lambda has to be 2x, and lambda has to be equal to 4y. Okay? And still, I need to have x squared plus 2y squared equals 8. The first equation here tells me that for that to be satisfied, I have 2x, lambda minus 1 equals to 0, lambda has to be 4y, and x squared plus 2y squared is equal to 8. So now we have some cases, which is that I can have lambda is equal to 1. In that case, the first equation is satisfied that it is 0. The second equation tells me that lambda equals 1. So here are my cases. If lambda is 1, so I'm trying to make the first equation 0, so I pick lambda equal to 1. If lambda is 1, then what is y? 1 is equal to 4y, or y has to be a fourth. And if I have y equals a fourth, then all of a sudden the function in g, that tells me what x needs to be. That tells me that x squared plus 2 times 1 over 16 has to be 8, or that x squared is 8 minus 1 over 8, and that is, what is that? 63 over 8. So x is the square root of, plus or minus the square root of 63 divided by 8. That's one pair of solutions. I took this to the other side, so I would get 2x lambda is equal, or 2x lambda minus 2x equals 0. and then take a common factor of 2x. So I get 2x times lambda minus 1. So in between here and here, I did 2x lambda minus 2x equals 0, and then take a common factor of 2x. Sounds good? So that gives me 2 points. The other possibility to make this equation be 0 is that x is 0. So what happens if x is 0? That's fine. I have an equation right there that is going to tell me that then 2y squared is equal to 8, and therefore y squared is equal to 4, and therefore y is plus or minus 2. Okay? So those are the points to try out. So now I have to evaluate the function at those points. So the critical points where plus or minus the square root of 63 divided by 8. That square root was supposed to be the square rooting everything. Okay. So I have the square root of 63 divided by 8, comma a fourth, and x is 0 and y is plus or minus 2. So now you just evaluate. The function itself was, it's right there. It's x squared plus y. So for this one, because the value of y is fixed, I do get, and this a square, I do get the same value of 8.125, but I have to be careful with 0, 2. If you evaluate the function at 0, 2, you get 2. But if you evaluate at 0, minus 2, you get minus 2. So this is the maximum value, and this is the minimum value. So the way I test for cases is I reduce the equations as much as I can, and then usually you reach one equation that is a product of things equals 0, and then this will be 0 if one of the factors is 0, and those are your cases.
Gotcha.
So typically either I do that, or in this case, I could also solve for lambda. In here, put 4y, then try to solve for x or y, and use the third equation, and then find the points that way. But here it's just easier to start from here, and then you have two cases, either 2x, so either x is 0, or lambda is 1. And those are going to give you two different cases, and that's two different ways to make that equation, that one equation, be 0. And now that equation is satisfied, and I have to satisfy the other equations and see what they give me.
Thank you.
Any other questions? Lambda is equal to 4y. This delta f, or this gradient f, was 2x1. This gradient g was 2x plus 2x 4y. I have to set them up to be parallel. And depending on how those are set up, you can put the lambda in either way. You're just trying to be parallel, so they have to be parallel vectors. They have to be a scalar multiple of each other. So in this case, I chose to do these equations. Multiply this by lambda has to be equal to this. This times lambda has to be equal to that, gives me this equation. And this times lambda has to be equal to that, gives me this equation. Yeah, sometimes it's more convenient to put it on one side than the other because it's easier to solve. It didn't end up helping me much, but I kind of like to have just already lambda be equal to 4y just in case. Yeah. Yes. Can we be a little quiet? I can't hear the question. I have to satisfy all three. So I look at all three and see where to start to make sure I can satisfy one equation and go from there. when there is an equation equal to 0, one of the factors on the left has to be 0, so that gives me something to start with, because that gives me two possibilities, and that's the two cases that I have here. So that allows me to start the sort of like investigating. So this has to be satisfied, but necessarily x has to be 0 or lambda is 1, and then I go from there to satisfy all three equations. All right, other problems. All right, that's a good question. So did somebody else say 4? Do you want all of 4 or 4C in particular?
Yes.
All right, let's try to do 4C. So I have a function, and they just give me the value at a point, and they give me the value of the gradient vector at one point. Okay? And we're going to try to concentrate on C. What is the rate of change of the function at 4, 3 when moving towards the origin? So what does that mean? I have a point, 1, 2, 3, 4, 1, 2, 3. Very not to scale coordinates, but this is my point 4, 3. And I want to know what the growth of the function is when I go in this direction to the origin. Okay? So I'm going to need a unit vector in that direction, but for now I want a vector in that direction. So if this is P and this is Q, which Q is the origin in this case, so this is the point 0, 0, how do I compute the vector PQ to start with? Terminal minus initial was the suggestion, so I'm going to do terminal, which in this case is the origin, minus initial. So it is minus 4, 3, right? 4, 3 would be the vector going to 4, 3, minus 4, 3 is the vector coming from 4, 3 to 0, 0. Now I need a unit vector in that direction. How do you do that? Yes, so I'm going to find, first of all, what is the length. So before I go into this, I'm going to find the length of PQ, which is the length of minus, by the way, I should simplify this to be minus 4 minus 3. So it's the length of minus 4 minus 3, which is going to be the square root of 16 plus 9, which is, 25, which is 5. Perfect. Okay? And then the unit vector is, the unit vector will be the vector PQ is scaled by the length of PQ. So it's scaled by 5 minus 4 minus 3. So it's minus 4 divided by 5 minus 3 divided by 5. Okay? Do you see what we did here? Which you have a vector and you have to divide by 1 over the square root of the sum of the coefficients. You have to do times 1 over the square root of a number. There's an article that came out recently in Scientific American of how the programmers for Quake 3 Arena, how many of you have played Quake 3 Arena? It's way before your time. How many of you, maybe Doom Eternal or something like that? Great, okay, some. So same creators. But back then, when they developed Quake 3 Arena, was one of the first ones, not the first one, but one of the first ones, multiplayer games where you have to keep track of where the players are, and the computer program was keeping track of players by unit vectors, knowing in what direction they were going, the position and the direction, but all of them were unit vectors. So they had to do a lot of 1 over the square root of a number many, many times. And the processing power was not what it was 30 days today. So they came up with some like very quick algorithm to find a approximation of that number to make that program really quick, to run very fast in computers. So anyway, if you go to Scientific American, look for the Quick 3 article. So we have the unit direction. So now I know how to compute a derivative in that direction. So now the directional derivative at 4, 3 will be the gradient at 4, 3 times the unit vector in the direction that I want. But I know the gradient. At that point, I do know it. It's 6, 8 given. And I have to dot it with the vector we found, minus 4/5 minus 3/5. And that will be minus 24. Whoops. This is a number, it's a dot product. So 6 times 4 minus 24 divided by 5 minus 3 times 8, 6 times 3, 24, 2 divided by 5, so minus 48/5. So that is the solution. Minus 48/5 is the rate of change in that direction. Yes. Part D? I don't have the room for it, but yes. Which direction maximizes? So to maximize the rate of change, the direction is the direction of the gradient. Okay, so that automatically is given here is the direction of 6, 8. They don't say give it to me in unit vector form, so it's just in the direction of the gradient. And since the gradient is 6, 8, towards 6, 8 maximizes. If you want to give it in unit vector, then you compute the length and divide by the length. So it will be this divided by the square root of the coordinate square. Yeah. It's the direction that maximizes the rate of growth in the function. So in a plane, we are in the plane, we are at a point 4, 3, and the gradient being 6, 8 tells me that in some direction, sort of like that, the function above it is in the direction that it grows the fastest.
So are we supposed to know?
Yeah, well, in this case, it's given. But if the function was given in terms of a function of x and y, I can take derivatives and figure out what the gradient is by taking the partial with respect to x, partial with respect to y, and then seeing what the value is at that point. That will give me the direction where it grows the fastest. Other questions? So when it is asking for a directional derivative, it can ask you find the directional derivative at the point, some point in the direction of, and then there are several ways that I can tell you what a direction is. I can give you a vector. First easiest is if I give you a unit vector. Second easiest is if I give you a vector of a direction, and then you have to find first the unit vector in that direction. And third, we can describe directions in many ways. So in this case, I described the direction in a little bit roundabout way that was from here in the direction of 0, 0. It could be what is the growth in the direction of, you are in a real life problem. If I am here, if I go straight in a straight line to Boston, what happens to the height in that direction? So it can be from 4, 3 to 1, 1, or it can be in 4, 3. We saw a problem in class where it was, if I go in the direction that is 30 degrees with respect to the x-axis, then what is the unit vector in that direction? I don't think we are going to be asking problems that are going to involve trigonometric values, so those would be given in this case. But directions can be asked in many different ways. Make sense? Other question? Yes. Part B. So I want to use the linear approximation at 4, 3 to approximate f of 5, 2. How do I do that? F of 4, 3 is f of 4, 3 is 5. And I have the partials at 4, 3 being 6, 8. And I want to evaluate at 5, 2. Okay? What is the linear approximation? The linear approximation, the formula for the linear approximation is the tangent plane, which is given by, so if I want to approximate at a point nearby, it's going to be the value at that point plus the partial derivative with respect to x at that point times x minus x naught plus the partial derivative with respect to y at y equals, well, it has to be at the entire point, times y minus y naught. Do we have all that information here? So I want to approximate at 5, 2, which is, close enough to 4, 3. It's just 1 unit away in x, 1 unit away in y. So I'm going to approximate at 5, 2. This is the x and the y. This is not x naught, y naught. F of x naught, y naught is at, the approximation is at 4, 3. So it's f of 4, 3, which is 5. Okay, I'm going to start filling in values. This. Okay, why is it not changing? There. This is 5, right? Do you know what the derivative is with respect to x at that point, at 4, 3? 6. Why is it 6? Where is it given? In the gradient. So the gradient itself, this number is the partial derivative at that point with respect to x. So this number is actually the number we need here. So this number is 6. Little x naught is 4. This number is also given by the gradient as 8. And this little number here is 3. So the whole thing is 5 plus 6 times x in here is 5, x naught is 4, plus 8 times y here is 2, while y naught is 3. So this is 5 plus 6 minus 8. So that is 5 and 6, 11, minus 8, 3. Okay? So all the information is sort of like hidden in the vector for the gradient gives you those values that are embedded in the coefficients of the linear approximation. For domain and range of a function, you have to be able to find the domain and range of function. I mean, let's see what's in the guide. For example, there was a problem that asks to find the domain. Finding the range can be a little tougher, but for example, to find the domain, you have to know that to find the domain of a function, I have to be able to evaluate the function is where the function makes sense. Okay? So we have things, for example, the square roots, the inside has to be positive or 0. In this case, x squared plus y squared is always positive, so that's going to be okay. The logarithms, the inside of a logarithm has to be positive. It can't be 0, it has to be strictly positive. You have denominators cannot vanish, right? We have other functions that are not defined at, for example, the tangent cannot be evaluated at pi over 2 because it becomes infinite. So functions that have, where those functions are also not defined, those are the things that are not in the domain. So in this case, for example, for part A, I need x squared plus y squared bigger or equal to 0 because it's inside of a square root. That is always true. And because of the log of 2x, I need 2x to be positive. So I need x to be positive. So the domain, in this case, is just pairs of x, y. And as long as x is positive, we are okay. That is this, but the y-axis is not included. Okay, so you have to be able to look for more examples of this type, where you have to identify where the function makes sense. That's what I would say. Yeah. Do you mean this? It would be nice, but if you describe the domain just by this, something like all x and y such that x is bigger than 0, I think that's fine. Yeah. Other questions? We still have 5 minutes, and I intend to use 5 minutes of helping other people. Yes? Number 1. If you are moving, please be very quiet. Yes? Any particular? Go ahead. Go through it? Yeah, so for part 1, when we are looking for vectors that are orthogonal, the easiest way to find that is using the dot product. The dot product being 0, that's what it tells me that A and B will have 0 dot product if and only if A and B are orthogonal. Okay? So I can just do the dot product of the two vectors, 1, 1, 4, C, 3, 4. That will be C plus 3 plus 4. So that is C plus 7. Oh, I copied it wrong. It's 3 times 1 plus 4 times 4, 16. Is equal to 0. So C plus 19 is 0. So C is equal to minus 19. So that is the value. There's only one value that makes them orthogonal. And then to find a cross product, I do my formula that says ijk 1, 1, 4 minus 19, 3, 4.